Hello, everyone, and welcome to the Switch Statement Podcast. It's a podcast for investigations into miscellaneous tech topics. Today's episode is about developer productivity and Charles Babbage's mechanical computers. Hello again, John.
Hey, Matt.
To the Switch Statement Podcast.
How's it going?
It's a podcast where we talk about pretty much anything that I think I said was defensively related to software engineering, programming, computer science. So this flavor of episode is show and tell, right? So we're each bringing something surprising, random. We don't know what each other are going to talk about. So what I want to talk today about is developer productivity.
Oh, okay.
So I feel like velocity. Yeah, I think that's another way you can look at it, and I think it's a kind of well understood to be a kind of a hard problem to do, is to like quantify developer productivity, and I kind of want to sidestep that because I'm not going to give any absolute ways to measure your own productivity.
Okay.
I tried to come up with like techniques that I think, let's say hypothetically you did come up with a good way to measure productivity. I think these would be techniques that would allow you to improve whatever that number was.
Oh,
right?
Wow. Okay.
And so, but it's not like, I'm not going to say like, oh, this is going to improve like lines of code produced by 50%. Like, I'm kind of trying to sidestep that part of the conversation. I've tried to come up with some things in my own career that
to improve your own productivity.
To improve my productivity.
Okay.
And I'd love to hear your thoughts.
Yeah, I mean, this is huge. So you're about to give practical advice on how to improve developer velocity.
Yeah.
Okay. Wow. I mean, I'm pretty excited about this. This is a topic that I care deeply about, I would say. But it's always a struggle. I've been doing this for a very long time, and it's still something that's just always top of mind. Every team is constantly trying to improve their own velocity. So let's get into it.
So the first thing that I think is really, really important is to ask for help. Like, I feel like it's just like the most difficult thing to do. And like, you're always thinking like, oh, like this is a stupid question, or like I should be able to just like Google until I find the answer to this.
Yeah.
I will be the first to acknowledge it's a continuum. Like, you don't want to just be immediately asking every single question that like arises.
Yeah.
But it's also an anti-pattern to just like struggle for like multiple days on a problem, which is something I have definitely done.
Oh
especially
yeah, me
earlier
too.
in my career. Like, I would just be like reading a tremendous amount of code and being like, how does this whole system work? Like, trying to figure out every single problem all on my own. And I think it was just terrible from a productivity perspective.
I agree with this so much. I think that software engineering has this like incorrect sort of foundational principle where like you should be super independent and like be able to like solve any problem. And it's to me, it's become so much of like a collaborative effort where, for any given problem, there's going to be someone who can solve that problem in like 2 seconds, either because they like wrote the API that you're using, or like, they're just wiser, they're, more familiar with the system. There's nothing wrong with just reaching out to that person and getting that super fast solution, probably learning things you didn't know about the system. It's just helpful. And also, people love being helpful. So if you're asking someone for help and they can, directly help you and like figure out what you're trying to do, like that's good for them too.
That feels good. Yeah. They like that. So just like from a practical perspective, like the way that I think about it is, it's important to be a little bit systematic about how you search for solutions at first, right? Like you should be Googling, you should be searching internal resources, maybe you have a Slack or kind of Google groups or what have you. Like you should try to, go through those resources, but then after a certain amount of time, and this is something you can tweak, but like, 30 minutes or what have you, you've been searching, like you don't see a really good thing, like just ask someone, because like you've done your due diligence, and like, and the other thing is they may come back and be like, oh, look over in this other resource or what have you. And then you can kind of add that to your list of like resources you should check before reaching out for help.
Yeah.
But yeah, so that would be the first thing I'd say. Just like don't be afraid to ask for help. No one's going to be judgmental. The worst thing someone's going to do is probably essentially let me Google that for you. Like style response.
Which, you will get that sometimes.
Oh yeah.
And it's frustrating. And I think that's another element to this is like, just be helpful. Like if you're the guy at your company who knows everything, like just help people. Don't be a jerk about it.
And I think you can give that response in ways that are not dickish.
Yes.
Like you can be like, oh yeah, like have you taken a look at the XYZ docs? Like they're awesome or what have you. And like, it kind of diffuses the situation. Whereas like some people literally will just like, let me Google, like send you a let me Google that for you link, and like that's just passive aggressive, and it's just bad. So don't do that.
And the other thing that I have realized, I have had the privilege of being like a senior person on a team that, a lot of people are asking me questions, and I figured out that if you do a good job of like, quote unquote teaching a person to fish, then people will ask you fewer and fewer questions. So that's another element. Like if you're on the other side of this, people are asking you for help a lot. Get better at helping people, and you'll ease your own burden. Right.
And kind of on the opposite side, it's like if you're concerned about the productivity of your team, like if you like belittle someone who's asking for help, they're gonna ask for help less, and like that's gonna be worse for like it's actually funny because I guess from like an outsider's perspective, like people could be asking for help less for potentially two different reasons. Like either you've done a good job and like they don't need your help as much anymore, or you've belittled them and mocked them and they're not asking for help because like you're negatively impacting their mental health.
Yes.
So just be aware that like you may not be able to tell the difference, I guess.
Yeah, don't be that second guy.
Don't be that second guy. Okay, so another super simple thing, I think it's a super powerful technique, is just beginning of the day, write down the 2 or 3 things that you want to get done in that day. You're probably like, okay, of course, like that's just so obvious, but it's like, I think it is useful to talk about kind of the mechanism there, where it's like, sometimes you have a little bit of downtime, and then if you haven't clearly articulated your goals for the day, now it's a little bit of a mental effort to figure out like, oh, what's the next thing I should work on?
Yeah.
I think it can be easier for you to like go down these productivity sinkholes where you're doing some nonsense while like you're waiting for a code review or something, where like you could maybe start to do something slightly more productive.
This is an exercise that when I do it, it definitely positively affects my productivity, but I'm just so bad at like the discipline of like every day just writing down 3 or 4 things. I also
trying to get better at, here we go, remarkable.
Yes. Yeah. I also have my remarkable. I've been trying to write my task list in it. It's also good to have like stretch goals. This is just, slight addendums to this, but yeah. And also like when you come in the morning, look at your previous day's goal, this sort of thing, like they carry over often. So very good exercise.
And there's kind of this other aspect to this, to like writing down your tasks. And I don't want to get too deep into this. If you really want to deep dive into like task lists, you should look into like bullet journals. This is kind of a whole like cottage industry essentially of like ways you can kind of manage your tasks. But it also helps you from letting things slip through the cracks. Like if you do a good job of kind of writing down what you need to do, and then you refer to the previous day's list of things you're supposed to do, like it's just harder for things to just like you forget something and you just don't do it. So but that that's like kind of less on the productivity and more like on your reputation as like a reliable human being, because like you say you're going to do something, and like even if it's not like critical to your day job, like you're making sure you're doing everything you're saying you're going to do.
Right.
Okay, so then I have produce and share your artifacts, even if they're not perfect. Send that design doc out. Like, I think it can be really easy. It doesn't even matter like what you're working on. It can be really easy to be like, oh, it's not perfect. It's not like I'm not ready to share this yet. Like I need this design doc to be like flawless before I send it out. And it's like, and that's it's an anti-pattern, and it's a pitfall and a fallacy that you can kind of produce this perfect doc. Like it's actually going to be much better for you to time box it, make it as good as you can, by the end of the day, but like send it out, because people are probably going to have like fundamental comments about the way that you're doing this, which is like, if you spend an infinite amount of time polishing this, like you're just going to have to, all that polish was for nothing, because like your core premise was flawed.
Exactly.
So
yeah.
It doesn't make sense. Like it's not worth the time to like super polish this design doc that you're working on, for at least for the first version. And like, maybe you don't want to share that with the entire team, like for the V1, but like it makes sense to get early feedback and like shop it around a little bit.
Yes, early feedback I think is one of the cheat codes of the software industry. Like once you realize that in order to build good stuff, you need feedback, you need to iterate. You need people who don't have tunnel vision, because whenever you're building something, you start to develop some form of tunnel vision.
Right.
And I've occasionally had extreme forms of tunnel vision where I just completely miss some detail, and you're only going to find that stuff by sharing it. So I think this is amazing advice.
This is kind of like sneaky productivity, because like it's not advancing your own productivity, but I think it's really important to eagerly prioritize reviewing other people's code.
Dude, you're so right. This is something that yet another thing that has sort of become more and more true as my career progressed is like, unless it's in the repo, it's has no value whatsoever. And that goes for your own stuff, but it also goes for your teammates' stuff. So you got to help your team get their stuff in the repo, get more eyes on it, get more feedback, get it into QA's hands so that they can break it and you can fix bugs as quickly as possible.
It's actually negative value. If you have code that has not been checked in, over time, like it actually swings from like positive to negative value, because you're going to need to do so much work potentially to like get it merged in.
Yes. Yeah.
Another one is like trying to understand the whole world, I think, is an anti-pattern, in a productivity anti-pattern. I think we talked about this before.
Oh yeah,
but
love this one.
Where I think you can get into a situation where you're like, oh, like I need to understand the system at this deep level all the way down, the whole system. And you can just spend an infinite amount of time exploring the code base.
Yeah. This is a paralysis trap. There's so many paralysis traps in computer science, and this is a really big one.
You have kind of a halting problem where like you'll just never, be able to deeply understand the code base on a level like that is maybe satisfactory.
Yeah.
So I think a better resolution is like you should start by being able to build the code, make some modification to the way the code behaves, and then you have this concrete direction that you can kind of show someone. You're like, okay, hey, like this is what I did. This is how I tried to solve this problem. This is what I'm trying to do.
Yeah.
And then you can show them that, and then that much more clearly articulates like what you're trying to do, how you're thinking about the system to someone else, and then they can be like, oh, actually, we have this other utility, and like I think it's just a much more efficient way to get feedback from another person than being like, hey, I'm trying to do X, Y, Z. I think it can be maybe harder for them to like give you concrete feedback if like you're like, oh, how does like widget X work?
Yeah.
Like,
that's one thing I wanted to add to this thought. This is another one that I completely agree with, but working with a system, like hands-on actually committing code to a system, is just a very good way to learn a system. So, and yeah, it kind of goes hand in hand with what you're saying, where if you're showing people concrete work that you have, it'll be easier for them to give you feedback. But it's just also easier for you to like slowly learn and understand the system as a whole.
Right. Or, I mean, if like, and I think in aggregate, like taking that approach is just faster. You know, you'll actually ramp up on like the way the system works more quickly.
Yeah.
If you try to do it that way.
In my experience, and I know I'm a specific type of person, but yes, like if I'm actively working in a system, I can learn the system way faster. It's so hard for me to learn a system by reading designs and, you know, chatting about it. Like I need to be working in it.
Yeah. And that's not to say that like, and that, you know, reading through the rest of the code is like not worth your time, because I think you kind of, as you go along, like your goal should be to understand the system at a deeper and deeper level.
Absolutely. Yeah.
But I think that, you know, doing a mix and not like needing to read like every line of code in the existing system before you start to make any change is an anti-pattern. Those are kind of like the high level things that I like to keep in mind as I'm like going about my day to day.
Yeah. And also, you mentioned a bunch of very effective, like you didn't call them out as bullet points, but in describing the other bullet points, you mentioned a couple things that I also think are super effective. One that you touched on a couple times is time boxing. Like time boxing, like learning how to time box and being strict about it with yourself is so effective. Like I have found that, you know, because it's so easy to, especially if you're working on something nebulous, it's so easy to just sink an entire day into something. So it's good exercise to think about how long a project should take, set aside that much time for it, and at the end, just share what you have.
Right.
And this kind of flows into a bunch of your other bullet points, but I think super valuable skill.
The other thing I was going to say is like, maybe you don't have a concrete resolution, but like sometimes you just have to be like, okay, well, this task is not high enough priority for me to spend more time on it. Like, and because I think it can also be, and I've also fallen into this trap as well, where you're working on a task and you don't want to not do the task. It feels weird. It feels like quitting to like not do the task, but it's actually really important to be able to say, you know, take a step back. Maybe you've finished the end of your time box and you're like, okay, how important is doing this really?
Yeah.
Because if it's not that important, it's another productivity time sink to continue to spend time on it, even if you haven't resolved it. So
yeah. No, that's so true. Yeah. Prioritization and proper time boxing help you focus on what's important. All right, welcome back. So I wanted to talk about something today that it's a completely random topic in computer science adjacent, I would say, and it's a historical topic, but I find this completely fascinating. So I hope you do as well. I wanted to talk about the difference engine.
Ooh, okay.
So this was an invention / mechanical device created by a dude by the name of Charles Babbage in the 1820s. And I'm going to be referring to my notes a lot because this is just a lot of information.
Dense, yeah.
So there was a couple things that I did not know about the difference engine. I think if you're in computer science, you've heard of the difference engine. It's a very early precursor to like modern computers. But I didn't know what the difference engine was for. And if I'm being honest, I feel like I still don't, even after reading about it.
Was it programmable?
So it was programmable in that the inputs were programmable, which I guess is not exactly programmable. And I'm glad you asked that question because there is another thing that will come up as part of this discussion, which I don't want to spoil it yet. Yes. Yeah. But anyway, the difference engine, the reason it's called the difference engine is because it uses the method of finite differences, which I don't know. Okay. I don't know exactly what that means. I think what it means is like if you have some continuous function, like an integral or something, or like sine or something, you can often represent it as like a polynomial or like a system of equations. Like, you know, sine can be represented as like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th. Right. So it's like this, it's an infinite sequence. But if you calculate the first like 9 terms of it, then you get like a very close approximation.
Right.
And I think that this is an example. First of all, finite differences, that equation that I just gave for sine, that infinite sum, is an example of using finite differences to calculate like a continuous function.
Right.
And this is what the difference engine was good at. And I think that, during the time that the difference engine was conceived and developed, there was some very important math for like calculating navigational, like if you're out at sea, like being able to calculate where you are based on whatever variables you have at your disposal. And like,
and so there would be some infinite series that they would have to describe the situation, and then they could use the difference engine to like precisely calculate the
exactly
or an estimate for that.
And it may not have been an infinite series. It might have just been like a complex polynomial that the difference engine could take polynomials of the form where, you have a bunch of terms with coefficients and powers, and you plug all that in, and it will compute the result. So I wanted to give some stats about the difference engine. The final difference engine 2, which there was also a difference engine 1, difference engine 2 is 8,000 parts. It weighs 5 tons, and it's 11 feet long on the longest dimension. And I was trying to estimate how like tall it is. It looks like it's about 6, maybe 5 or 6 feet tall. So it's huge. Okay. It's like an enormous thing. And as you crank it, which, by the way, cranking was extremely difficult because you're turning like hundreds of gears, maybe thousands. I don't know. I guess it's 8,000 parts. So
nice. So in order to be a programmer, you need to be like a real beefy dude.
Yeah, exactly. But basically, in order to achieve one crank of the machine, you actually had to crank it 4 times because they had to add all these additional gears for like mechanical advantage and stuff.
Right.
The machine produces printed output, which I did not realize. I thought that was cool. I watched a video. There's like a very cool printing mechanism that like it prints the output onto this. It basically looked like plaster of Paris, so that you could then like, put ink in it and press it against paper and produce tons of copies or whatever.
That's amazing.
Yeah, it was crazy. It looked like this extremely complex mechanism just for printing. And then obviously, the difference engine itself is this like amazingly complicated like system of gears and stuff. Another thing that I thought was very interesting was jamming was actually a form of error detection. Like there was a couple cases where it would not be able to find a value. Like there would be a value in between 2 integers or something. And what it would do is a gear would turn halfway and then it would jam. Like the machine was like designed to jam in order to tell you that so there was something wrong with your like initial input values, which I found super interesting. It's like kind of early mechanical error detection.
That's kind of amazing. I mean, I guess that makes sense. Like you got to communicate somehow, and they didn't have like error consoles, I guess.
Yeah, so I thought that was super interesting. I also wrote down, this is like a total tangent, but I also wrote down the earliest mechanical calculator, because the difference engine is considered to be a mechanical calculator. The earliest mechanical calculator is thought to be this thing called the Antikythera mechanism.
Oh, yes.
Which is amazing. If you've never heard of the Antikythera mechanism, like Google it. It's amazing. It was designed, they think it was created during the Hellenistic period, which is 323 to 31 BC.
Yeah, didn't they find it on the bottom of the ocean or something, like in the Mediterranean or something?
Yeah, you're right. And it was for navigation. So they're assuming, it was on a ship because that's where it would be, and the ship sunk. So they found it at the bottom of the ocean, and it was a very incomplete
so apparently
thing.
It didn't work very well.
Well, who knows? Maybe it worked really well, and then pirates wanted to take it or something.
Right.
All right, but anyway, back to the difference engine. So the project is actually considered this massive failure historically because, Babbage designed the thing, and he was like, let me build this. The government gave him about 17,000 pounds. This was England, which is about $2 million today. And the machine was never actually finished. There was a lot of issues with like, they couldn't, just the technology to like create parts at the time. This machine required all these very finely tuned parts.
Now, this was Difference Engine 1 or Difference Engine 2? Like,
that's unclear to me. Like, so Difference Engine 1, I think, is the one that he spent the most time building, and he had this contract with the government to like figure it out. This is another issue with the project is Babbage could not focus, it seems. He was constantly thinking of new things. He conceived of Difference Engine 2 like while he was working on Difference Engine 1. So I think a part of the reason the project sort of flopped is because Babbage himself was, it just seems like he was a little bit whimsical. Yeah. But yeah, he did finish a chunk of Difference Engine 1. It's a piece consisting of about 2,000 parts, and it was assembled in 1832. And apparently it still works to this day, and it works flawlessly. So it wasn't any shortage of like actually being able to do it. It was just, other
focus.
Yeah, focus and, probably not enough capital, or I don't know. But the fact of the matter is he was able to build a pretty sizable chunk of the thing that worked perfectly.
What was this made out of? Did they have steel at the time?
That I don't know. They built one in more modern times, and that one is made out of like very nice materials like steel and brass and stuff.
I think that's the one I've seen, which is
Yes.
probably it's probably like coloring my image of what the original one looks like.
There was also one that was built where they intentionally used the technology and materials that would have been available in Babbage's time, and they were able to do it. So yeah, again, that's just more proof that like his designs were sound. The designs that he came up with were sound. Although, just a super interesting tidbit about his design. Apparently there was flaws in his design. Like they still have his designs to this day. So they went over them in order to create these modern day difference engines. There were flaws. They think Babbage introduced those flaws in the designs in case they were stolen, which I just thought was really interesting.
Really?
Yeah.
So he knew of a couple of like targeted flaws, and he would have to just unflaw that one little section
Exactly.
when he was building it himself.
Yes. So he kind of had his own, little code in the designs themselves.
DRM for the difference engine.
Exactly. All right. So that actually transitions nicely into this other concept. I mentioned how Babbage was, sort of famously whimsical. He was a serial inventor, just constantly coming up with amazing ideas. He came up with this thing called the analytic engine.
Right.
Which
Difference Engine 3.0.
Exactly. So this goes a step. Actually, saying a step is kind of an understatement. This goes far beyond the difference engines.
Leap.
Exactly, a quantum leap. This thing originated the concept of a digital programmable computer. Like it's commonly credited, his initial designs and his initial conception of it, commonly credited with kind of originating that notion. So, I mean, this is huge.
Now, when you say digital, what do you mean by that?
Like ones and zeros, and being able to compute, use math basically,
Right.
and also have like some discrete output or an output that's represented by like a series of digits or something.
Now, this is still though made with the same thing where it's just a bunch of gears and stuff like that. Right?
Yes. So this was a physical device, but
Right. So why doesn't that make it like? Because I feel like I think of two. There's the two things. There's digital and there's analog. Right. So it's like, can it be analog and digital simultaneously? That's what it sounds like.
that's an interesting point. I think it was digital because it dealt purely with finite
Like
digits, like integer values. I mean, it could represent decimals, but it would always be representing decimals with integers, basically. So I think that's where the digital
That's its own massive topic in computer science, which is like crazy. He must have had a floating point representation of numbers.
Yeah, he I don't know if he pioneered a lot of this stuff, but this thing had a lot of like extremely interesting, software engineering concepts built into it. So the analytic engine had flow control. It had this notion of storage where it could store values and then continue computing based on those values. It had a notion of procedures. If you look at the Wikipedia page, someone came up with like a language where you could actually write code that could be like directly translated to something the analytic engine could use. And they like wrote the Fibonacci sequence in like analytic engine code. It's totally amazing. And I thought this was an interesting quote. Babbage is also kind of a gold mine for quotes, in case people are interested in that sort of thing. But he has a quote, and this is referring to the machine being able to use its own output. He referred to that as the engine eating its own tail, which I thought was pretty cool.
Yeah, a Ouroboros.
Yeah, exactly. And it kind of reminds me of like, I don't know, I feel like in computing you see the word tail a lot, like the end of a list or tail recursion if you recurse at the end of a function. And I don't know, I've always liked that sort of imagery.
Right.
Okay, so the actual difference engine was built based on the original model in 1985 to 1991. And this is where I wrote the note about there was several fixes to the designs, but people theorized that they weren't real fixes. They were intentional mistakes that Babbage put in the designs. Mm-hmm. And this is mostly based on the fact that he was able to build a working, device back when he was designing the thing. So it's pretty clear that he like knew what he was doing. And yeah, that's about it. Like I think this is something that we could discuss for a billion years. I'd love to learn more about how the thing like actually works and what its actual like purpose is. Like I'd love to learn like during the time, what would someone actually use this thing for?
What did they want to do with this?
Yeah.
Was he just building the analytical engine for shits and giggles? Like, did he just think this was like an awesome idea?
Yeah, I think he could just see that this would have so many practical uses, that it was just this utterly amazing thing that needed to be built.
This is crazy to me because it just goes to show you that the world doesn't necessarily always like pick up on good ideas, because like it's just this island, this like ingenious island that like no one really, it's not like everyone immediately realized that this was an amazing idea, and they like, because he had the designs for the analytical engine, it never got built.
Yeah.
And then like I feel like we haven't heard really anything about like physical computation in the interim, and then we just got to the digital revolution until like in punch cards and things like that, which didn't really bear any like direct relation to the Babbage's work.
Yeah, and if anything, the government was aware of it and kind of abandoned it.
Yeah,
which is even furthering your point of like they actively turned their back on the idea. So it's pretty interesting. I guess they just couldn't see the extreme like practical usages of such a machine. So there's this is Babbage speaking about the questions that he's been asked about the machine. Obviously, while he was developing this machine, people asked him all sorts of stupid questions.
Right.
So this is one of them. He says, "On 2 occasions, I have been asked, 'Pray, Mr. Babbage, if you put into the machine wrong figures, will the right answer come out?'" And Babbage says, "I am not able to rightly apprehend the kind of confusion of ideas that could provoke such a question." Which I think is just the most, I don't know, awesomely like somewhat passive aggressive, but just amazing way to like put someone in their place. Right. But it also just does speak to this, this common element in software engineering, which is there's a lot of people who don't understand, the underlying mechanism. Not necessarily because they're stupid, but just because it's complex and it might not be what they devoted their life to. Right. But they might, they might be on one side or the other based purely out of like emotion rather than some underlying merit.
Deeper understanding. Yeah.
Yeah, exactly. So, yeah.
Okay. Very cool. I think we should go back. I think we should go back to the state of the world where we were building physical computers.
It's so cool. So. If you get some time, check out the videos, because there is a differential engine too. It's working. It's in a museum somewhere, and you can literally plug values into it, see it function. You can see it like carrying ones when it does like, when addition goes past 10 or whatever. It has these crazy elevators that like lift these physical things up and kind of carry ones. So
that's amazing.
You should check it out. It's really cool.
I will do that. All right. Well, I guess that's all we got for today. So I think we'll call that another another episode of Switch Statement.
Heck yeah.
All right.
All right.
Peace.
See you later.